Okay, so last time I taught you the what we call the LU factorization. Let's see. So we have what we call the LU factorization. So the LU factorization is just you want to factor matrix into two matrix multiplication. Okay. There are two guys. Okay. One is called Mr. Doolittle. So Mr. Doolittle, he proposed that the matrix L, okay, since the unknown, okay. Oops. The unknown of the matrix of this more than the restriction that we have, okay? So Mr. Doolittle, he proposed that instead of these L11 and L22, just any number, he fixed it so that it is 1. So Mr. Doolittle come up with the method called LU factorization, with L is the unit lower triangular matrix. Okay. And the other one is Mr. Kraut. Mr. Kraut say, okay, why have to do the same? Okay. So then he will use U as the upper triangular unit, upper triangular matrix. So you have two ways to factorize. And someone might ask, can I leave it as something else? I say that you have to fix, okay? But you can choose your own. You can use pi for L11, L22. But why make your life harder, right? Because number one is easy to work with. So we stick with number one, okay? So I think that this one is called the factorization. Once we have the factorization, what we try to do, we try to replace matrix A by substitute A or replace A by matrix L times U. And this allows us to solve to get the solution. Only 2 steps. Okay. So because L is the unit lower triangular matrix, so we can solve, we can say that, okay, we have L times U times X. So we will let U times X equal to the new unknown I call Y. So I have the system L times Y equal to B. Since L is the lower triangular matrix, we can get the solution. We can solve for Y easily by using the forward substitution from top down. Okay. And then once we get Y, we plug into the right hand side here because we know that we set it originally that U times X equal to 1. And then U is upper triangular matrix. So upper triangular matrix, we use the backward substitution. So we get X. Okay. So we have the solution. And last time I showed you that we use the for Doolittle factorization, and the homework is for you guys to factor this as the Kraut factorization. Okay. So that's all we have for the solve the matrix. And the first group, okay? The first group of the method for solving the system of linear equation. Actually, I have to tell you that there are 2 types, okay? System. The first one is we call the direct method. That includes LU factorization, Gaussian. Okay, LU factorization. That is one way. And people sometimes use the direct method because that leads to the solution directly. Okay. The second type of the method for solving this is called the iterative method. Okay. Iterative method is the other things that we will focus on. Okay. I will teach you two methods. Jacobi method, and the other one is still have the name Gauss-Seidel. Okay. The idea is this: why it is called iterative? It's when we will repeat the same process. Okay, repeatedly. Do it, put it in, get the result, put it in, get the result, put it in, get the result. We keep doing this, okay? Let me show you example. We have, for example, 3x plus y equal to 2, x plus 4y equal to 5, okay? So now, if you write it out, you will have the system like this. I will have 3, 1, 1, 4, and the right hand side is 2, 5. If we do direct method. Okay. Now, if I guess that, well, I will do what we call guess the result. Okay. What I want to do is the solution of the system is mean whatever you have on the left hand side have to be the same as the right hand side. Okay. So this is what we want to do. So I will rewrite, I will take the first equation. And I solve for x. I use the first equation. I will get x equal to 2 minus y, and then divided by 3. And for the second equation, I solve for y. I have 5 minus x divided by 4. Okay? Just simply write something that the system have x, y on the left hand side, and on the right hand side also has the variable x and y. Okay? What you want to do is I will just say, okay, if I guess that I plug in something here, I say initial guess. I will say that initial guess, okay? And then I plug it in. I will get the new number x1, y1, okay? And then if I said if whatever I plug in is the same as, if it is the solution, what does it mean? This x has to be the same as this x, right? If it is the solution, because you have only one solution, right? So you want the values x and y, then plug it in and make your equation equal to each other, every equation. Does it make sense? So I make initial guess, I plug it in, I get x. I plug it in, I make the initial guess vector x. I have to say that composed of x0, y0. This is just basically guessing. And then do this multiplication, this in the box, okay? Like input, plug it in, you get output, okay? And you check if input is the same as output. If you plug it in, input equal to output, you're done, okay? But how about if not? You get the input here, plug it in as the new guess, guessing the new values, okay? But you have the systematic ways of guessing by taking the result. So I will say, okay, the second step, I will plug in whatever the output that I have. If it gives you the new values, it's not the same, right? It's not the same and it's not the solution. So you do what? Keep doing this until whatever you plug it in, 2 minus y, plug it in n, maybe. Whatever I plug it in, it gives me close to my input. I will stop, okay? And the question is when stop, right? When stop, when we have vector x n minus x from the previous step, you take the maximum less than some value, small value. These small values may be 10 to the minus 5, 10 to the minus 6, 5 times 10 to the minus 16. It's up to you. But you want whatever you plug in close to the output, okay? And here I use this notation, this mean, okay? If I have vector x composed of x1, x2, xn, then this notation is gonna be the maximum over I between 1 to n of the absolute of xi. Okay? You take the maximum, only the largest one. If you can control, you have x1, x2, suppose you have thousands of them. You pick the last one, the largest one. And if the largest one less than what we want to have, it means you can control other things, right? Because other one less than the maximum, it means every term will be less than what we want, okay? So in mathematics, we call the maximum norm, or we use to calculate the length of something, the distance of the one from previous and the one that we just got, okay? So this one, I will be able to write down the general. This is very easy, okay? I can teach this topic, finish in 15 minutes. Okay, because it's easy, right? What you want, you have the scale, you plug it in, is get you the new result. If it's not, you plug it in, get the new result, plug it in, get the new result, until what? The left-hand side equal to the right-hand side. That's it. If you get close to each other, you're done. That's it. Okay. So I will write this down mathematically. Let's see. I use the iterative method here. I will say that if I plug in the input n, I will get n plus 1, new one, right? Plug in, okay? And n start from 0, 1, 2, 3, and so on. But you have to finish at the maximum. This maximum is controlled by you. It's controlled by you. You will say that, okay, I will let it run up until only 1,000. You say that 1,000. But if you want more accurate, you said, okay, I allow 10,000. You, programmer, you decided, okay? You, the one who decided. Someone say, okay, 100, that's enough for me, okay? You don't need to go that far, that's fine, okay? It depends on the accuracy that you want to use, okay? If you want a high accuracy, you want it more close to your solution. You want the accurate result, you set this. And also the other one you have to set is the maximum x sub n plus 1 minus, okay, n less than epsilon. If you want it only 3 digits, you might say, okay, less than 10 to the minus 3 is 3.5, 10 to the minus 3. You want it less than 3rd digit, something like this. Okay. Or you will say, okay, 10 to the minus 16 for more accurate result. Okay. So this is called the tolerance. Tolerance is mean how much you can tolerate or how much you can accept it. Okay. So it's assigned by you. Okay. So that is very simple. So now I will use Microsoft Excel to find the solution. Okay. 3x plus y. Let's see. I will find roughly of the solution. Okay. So it's 3x plus y equal to 2. This is this graph. And the other one is x plus 4y equal to 5. So it's cut here. Okay, you have two equations. This one is that's one. Okay. This one, the one here is equation number 1 is equation number 2. What is the solution? Okay. The intersection point is 0.27 and 1.18. This is roughly speaking by using the GeoGebra. Okay. Now I will do it if we don't have these two. If we want to do it, I use Microsoft Excel. Okay. I have the new one. I input maybe 1, 1. It's my initial guess. Okay. And xn plus 1, if you look at the formula, xn plus 1 is 2 minus yn y. Okay. That's, I guess, is 1. Maybe, okay. And divided by 3. And for y, the new values come from 5 minus x from the previous step divided by 4. I input 1, 1, and my result is this. Okay. And then I copy. I input 3, 1. My result is 3, 1 point, this one. I input this, I get this. I input this, I get this. This, I get this. If I say, okay, if I look at only 5 digits, suppose I look at 5 digits, when should I stop? I plug in here and outcome is here. For y is very close, okay? If I'm not satisfied, I do one more, I get this one, I input step number 10 to get step number 11. I get this one. In and out still a little different, right? If I say, okay, maybe here I stop it, I get the result that whatever I plug in and I get the result. Okay, is that easy? Yes. Okay, that's a lot of engineering people work on. They use the iterative method. Okay, just have the equation. So for x, y, and z, and for example, and then put have x and y on the right hand side. Okay. And now let me go back to other problems. Now I get, okay, Ajahn, this is only 2 by 2. Maybe it's easy. Maybe 3 by 3. Okay, 3 by 3. Three by 3. Okay. X plus y plus c equal to 1. Okay, maybe 3c. I don't know if I can find the solution here. Okay. Maybe I'm going to change it to 5. Okay. Suppose I have this. Let's see. I start with x and I solve for the first equation. I start with x. I have 1 minus 2y minus 5z. Second equation, I get y equal to 2 minus x minus 4y, and then divided by -1. And the third equation, z equal to, no. Y no. I'm sorry, caught the cold. I have on my cold medicine. Okay, sorry. Just 1y, right? Am I right? 2 minus x plus z divided by 4. Okay, that's right now. Z is 3 minus 6x minus 2y divided by negative 10. For this Jacobi, we make the initial guess, okay, and plug it in. So I will say that this is, maybe I say it is n, 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 n. To get the new result n plus 1, use the, to get the new result n plus 1. Okay, everybody get it? So I will work this one in Microsoft Excel, okay? Let's just make the guess. So maybe x0, 1, y0, 1, z0, 1. You just guess what would it be my for the solution? What? One, one of one, one. Xn is 1 minus 2 times y from this one, yn, minus 5 times zn. Yn equal to 2 minus xn plus zn divided by 4. And this I get 3 minus 6 times x is this one, x minus 2 times y, this one, divided by negative 10. Okay. Okay. And then I gonna do this, copy, plug in and get out, plug in and get out. What's wrong? Number getting, oh my God, it's getting larger and larger. Did I do something wrong? Let's check. X1 is 1 minus 2, Y, which is the blue one, minus 5 times the red one. Okay. Yn 2 minus x plus z divided by 4. 3 minus 6x, x is blue, minus 2 times y divided by minus 10. Oh, this doesn't work, right? It's getting larger and larger and larger. Okay, I'm sure that this Excel is correct. And what's the problem? What's the problem? What do you think? What's the problem? Why is getting larger and larger? Do you remember that when I said like we work in the floating point arithmetics? Okay. The most scary part is whenever you multiply something by the number which is larger than 1. Okay. You see, this z is multiplied by 5. If I input 1 for z, suppose z, the solution, I don't know what it is, I get the error. I multiply by 5, the error gets larger and larger and larger. Right? It's going to be the first time you multiply by 5, second time you multiply by 5 square, third time you multiply by 5 to the third, and this number multiplies getting larger and larger. That's why this is very scary part. But if I want to do this problem, I have to manage. Try to make the multiplier some number that multiplied by x, y, and z. I want to control it. I want that number to be less than 1. Okay? So you don't want something like this. It's scary. This is scary. This is scary. Other thing is okay because it's just a fraction. Right? 1 over 4, 1 over 4, 6 over 10, 2 over 10. So this one is fine. Okay? So how can we do it? So we will try to see that, okay, if I look at this one, number 6 is the largest, or is here, x, this is z. This problem, we have to trick a little bit, but I will show you, okay? That mathematician, we know that if you have some number which is greater than 1, multiply it, so your scheme will blow up, okay? No solution. So we try to find the structure that your iterative method will guarantee to have a unique solution, which means to converge to the solution, okay? So I would like to introduce you is called the strictly diagonally dominant. Okay, so it's strictly. So from now I will say it's SDD. SDD is if the matrix is SDD, it means strictly diagonally dominant. Okay. So if the matrix is SDD, what does it mean? It means that the magnitude of the element along the diagonal, I call it AII, greater than. This means just the strictly is give me the word greater than, no equal sign. Strictly diagonally dominant is mean greater than the sum of the j not equal to I of Aij. Okay. It means that in the same row of the matrix, except the one that in location, if you look at the first row, I is 1. You look at the first element, A11. A11 have to be greater than the sum of all element in the same row. Okay? I give you example of the strictly diagonally dominant. Okay? Now, if I look at my first row, I will get that 1, 1, which is absolute part greater than 1. If I look at the second row I have absolute of -6 greater than 2. So this matrix is SDD. Okay, I just introduced you the matrix. Let's see. If I have matrix B, so now you look at the element here. You have absolute of -10 greater than 1 plus 2. This one, you have absolute of -5 greater than absolute of -3 plus 1. Okay? And the last one, 6 . So this is called the strictly diagonally dominant. Okay? They will say that if the quotient of your matrix AX equal to B, okay? If matrix A is SDD, this will imply that your iterative method will converge to solution with any initial values. Okay. It means that if you have matrix A that satisfies the strictly diagonally dominant, okay? No matter you pick the initial case, you will end up having your solution. You hit the point, okay? With this good property. So if you have the matrix, okay, the one that I gave you is not nice, because you can see that this is number one, not strictly diagonally dominant, right? Okay, so let me just show you that, okay, if I have some problem with strictly diagonally dominant 3 by 3 iterative method, this will work, okay? The first example is does not work. Okay. If I have maybe 10x plus y minus 2z equal to 1. So you can see that 10 greater than 1 plus minus 2. Okay? Because the quotient 10 is greater than the sum of the rest. Maybe 2x now you know that absolute minus 6 greater than 2 plus 1. Second row satisfied. Number 3, we have x plus 2y minus maybe 4z. Okay, suppose this, I will see that this matrix, quotient matrix is strictly diagonally dominant because this is the largest number. If you have strictly diagonally dominant, why it is converged? Because this guarantee that your multiplier will be what? Less than 1, right? So this will guarantee that if you solve for x using the first equation, 1 minus y plus 2z, and then you divide it by 10. So you see, you divide it by 1 over 10, you multiply by 2 over 10, which is less than 1. Okay. And then the second equation, you get y equal to 3 minus 2x minus z divided by negative 6. And the last one is z is 2 minus x minus 2y divided by negative 4. For Jacobi method, you will say, okay, I make a guess, put in on the right-hand side, every term, I plug in the guessing values, I will get the new one. Okay, very simple. I have strictly diagonally dominant matrix. I solve for x, y, and z. This guarantee that the multiplier less than 1. Okay, and then from the theory say that for any values of the initial guess, it will always converge. Okay, let's try. Okay, let's try. I start from 1, 1, 1. Okay, 1, 1 minus y n plus 2 times z n divided by 10. This equal to 3 minus 2 times x minus z divided by -6 equal to 2 minus x, well, x here, minus 2 times y. Please help me check, okay? Minus 4, okay? 2 minus x minus 2 times y equal to this. And then I copy the formula. Okay, 26 iteration. I plug in this number. Okay, no, that's not right. Yeah, I plug in 0, get this result, and this one, 45 iteration. Okay. Let's see. If I change, what do you want? 100 minus 2. 1 is 0. Okay. So just any initial guess. It will converge, but it's not. Okay. It's not the same iteration. It depends on how you want it. Okay. So this is like plug in 0 and get this one. It's no matter how you input your initial guess, you may put in 0, 0, 0. You get what in, what's come out, the same. Okay. So it's kind of nice that if you make sure before you do it that your matrix is strictly diagonally dominant, this will guarantee that your multiplier less than 1. So when you do iterative method, it will converge. But this one you see is in the old day. They don't have calculator. They don't have calculator. You have to do it by hand, right? Even if just multiply and divide the number is still a lot of effort. So they think that, well, how can we make it faster? How can we make it faster? This is the way that here, this is like the row. You always use the one on the top row. It is similar to say that, okay, you allowed to go to leave, okay? If you finish the quiz, for example, suppose, okay, you have to wait, okay, the first row do first. I give the first row to do it. And they said, okay, the next row can come in, only everybody in the first row finish. Okay, that's the purpose of the Jacobi. But I say, okay, if number 1 finish, they leave the room, empty space. What you do? Second row, the first one come in. Okay, or whatever is finished. Okay, you use the values that already update as the new values. Okay, so for this one, you wait until this finish the first row. You make the first row finish. And then the second row calculated by everything from the first row. Second row, you finish it. Everybody, the third row here, second iteration, you use everything here. But why don't we just, okay, here you have no choice. You have to use the one above, right? So you get this cell. You get this cell. This cell already calculated. Why not use it? Use that number. for the calculation for the next step to calculate y. Because y had to use the blue one on the top. But we have this blue one, right? We have this cell already calculated, okay? I will update use it. So that is what the Gauss Seidel two people, okay, brainstorm, you get the faster algorithm, okay? Mr. Gauss and Mr. Seidel together make the faster scheme of this iterative method. So he will propose what we call the this is called the Gaussian. No, Jacobi. Gauss-Seidel will say that, okay, come on, we do the same thing, except that, let's see. Okay, I make initial guess, plug in here. I get the new values x, but this x is updated already. You get the new values, right? So to calculate y, if you want the new values of y, instead of use the previous one, x sub n, I will use x sub n plus 1. Okay? Because you already got this one update. You plug it in right away. How about z? Z, you still don't have the new one, you use the old one. Does it make sense? Because you get the new values, you use it. You take advantage of this one for granted. So now you get x and y. Once you get x and y here, you come, this one, x, you get the new values, use it. How about y? Do you get the new values? You use it. And then you will get the new z. Okay? It makes sense, right? Whatever is finished, you use it. It's gonna speed up. You don't need to wait until everybody finish and use the update. Okay, so it's gonna be faster. Like you can think about, you allowed to do one row at a time. So if someone finish, you take over. Okay, you take over that. So now let's just use this calculation. Okay, let's use this calculation. Okay, this is my previous one. I will do the blue one. Now that's what I'm working on. I use the green one, okay? So I'm start with my initial guess, the same thing, okay? Initial guess 0, okay? This, okay, I just do it. 1 minus y over 1 plus 2 times z, then divided by 10. I got it. 0.1, the same thing. And this cell equal to 3 minus 2 times x. X, since we know it, I use the one in the front. Okay, at the same level, xn plus 1. Minus z. C, we don't get it. We use the one above. And then divided by negative 6. Get this one. Okay, z is 2 minus x. Oh, x. I should use what? We have x in the same level. Xn plus 1. Minus 2 times y. Do we know y? We know it. This one. Divided by negative 4. We will plug it in this one. We do the same thing. Okay. So this one, use the one on the previous step above. This one, use x here. Just the new updated. This one, use x and y in the same level. Oh, I made a mistake again. 1 and 2 times 4. Okay, so this is correct. And then do the same thing here. This we use 2 above. This we use x in the front. This we use x and y in the front. Okay, so now I copy. Here you can see 15 times is converged to the solution. Whatever get in, and we get whatever get out. And we get the same. But here we take 40 to 43 steps. Okay, so it faster. In a way, it makes sense, right? So you update the new value. So this one you have only 14 times. So this is how we say that this one is the Gauss-Seidel method. Okay. So today I teach you 2 methods. One is Jacobi method. The second one is Gauss-Seidel method. But those 2 will converge only if the coefficient matrix is strictly diagonally dominant. Okay, it means the element along the diagonal greater than the absolute of the diagonal, greater than the sum of the other terms in the same row. Okay, that is called SDD, strictly diagonally dominant. But if, for example, if it's not, let's see, for this one. For this one, okay. Oops, sorry. Okay. Before we finish today, okay. For this problem that we start with, that we got the diverge, we didn't get the solution. This one, as I said, is not converged, right? The thing is this term, right? So other thing is 1 over 4, 1 over 4, 6 over 10, 2 over 10. This one is fine. Okay. We can think about swap the row, interchange the row. The solution doesn't change. If I say, okay, x is the largest here, if I swap it, but it still doesn't strictly is diagonally dominant because 6 less than 2 plus 10. Okay. So I will try to make this number larger than the sum of this. Okay. I can add something else. Okay. This one, 2 plus 5 is 7. Okay. I can 8 or 9 here. I can have, okay, let's see. Okay, since this is the equation, I have this 1, 2, this is 5, is 8. So you have add or one more, okay? Okay, I add two of them. When I add to have add on the left and on the right. The solution should be the same, right? Because I add only 8x. So on the left, I have 9x. The first equation, I have right? So if I solve for x, I will get 1 plus 8x minus 2y minus 5z, and then divided by 9. You see? You will see that all the number you have divided by 9. So you have 8 over 9 is still less than 1. 2 over 9, 5 over 9. Okay? And then for the second equation, it's okay. 2 minus x plus z divided by 4. And then we have z equal to 3 minus 6x minus 2y divided by negative 10. Okay? One more, I show the result of this scheme. Okay? Both Jacobi and Gauss-Seidel. So if it's Jacobi, let's see, okay? This one is 1 plus 8 times x. X is here. X minus 2 times y minus 5 times z. The whole thing divided by 9. Okay. This one is 2 minus x and plus z, c from the previous, divided by 4. This is 3 minus 6 times x minus 2 times y divided by minus 10. Okay. Suppose this one. Okay. So I get the solution is this one. Okay. So I get the solution is this one. For the Jacobi use 32 iteration. Okay. Now, let me copy this one. So this Instead of use x above, so you use x below, okay? X below. And this, instead of use the blue and the red there, so you use the one in row number 3, H in row number 3. Okay, so you see that is Gauss Seidel. Whatever input, you get the result out of that. But on the left is the blue one, is you did not use the update. You use the Jacobi. The one on the green one is convert faster in the 2526. So you use the Gauss Seidel method, which is obviously technically you get converts faster. Okay, so this is what we have for today, and then I'll see you guys Friday. Okay, all right, have a good day. I will assign the homework soon. Okay. Again.สวัสดีค่ะ